Great. So welcome everyone to this week's Math Physics seminar. We are delighted to have Vincent Vargas from, I guess, Marseille and University of Geneva. He will give a talk about Liouville conformal field theory and a probabilistic construction to the bootstrap solution. The floor is yours, Vincent.
So thank you very much for the invitation. So sorry, I mean, on the slides it's written Rémi Rod and Vincent Vargas because I recycled I recycled exactly the slides for the talk we gave at IAS just a few weeks ago. So we gave a joint talk and it was kind of longer. So I encourage you, if you're interested in this talk, which is going to last 1 hour, I encourage you to go at the IAS on the IAS webpage where we gave a similar talk, but in 1 hour and 30 minutes. So we had more time. And so what I'm going to explain is a joint, a program that we finished with, so Rémi Rod, who's in Marseille, Colin Guillermou, who's a specialist of spectral theory, PDEs and all that in Orsay, France, and Antti Kupiainen, who's a mathematical physicist in Helsinki. And so let me also mention that recently we were joined by Guillaume Bavrez on new aspects around our program, which I'm going to try to describe to you today. Okay, so roughly our program is I mean, it's in the title. We have two constructions of in the literature at least. I mean, there were two constructions of Liouville, and we tried to unify them. And this is what I'm going to explain. Okay, so let me first give you a bit of the context of all these conformal field theories, etc. So on one side, you have statistical physics models in 2D at critical temperature. Now here, I mean, it's the world of statistical physics, or if you like, the world of probability theory. So these systems are described by what one could call discrete Fineman path integrals, discretized path integrals. And on the other side, you have what is called conformal field theories, which in their modern form were described and constructed by Belavin-Polyakov-Zamolodchikov in 1984 in a landmark paper. And so these conformal field theories are based on not on probability theory, etc. Their construction is based on representation theory, and so BPZ. So these three authors, they spelled out a way of constructing and computing conformal field theories, and they called that the conformal bootstrap because it's based on a recursive method. So you know, in conformal field theories, you have fields and you want to compute correlations. And if you do that, you have to, their method enables to compute them recursively. So start with the 3-point function, then the 4-point is constructed by some kind of general procedure. Okay, and so soon after this BPZ paper, which is a physics paper, mathematicians soon wanted to, spell out their own axioms, really in a really rigorous form, to try to recover this conformal bootstrap formalism. And that's what people did. So let me mention a few names. There's Gavitsky, there's Segal, which is going to play a key role today. There's all these vertex operator algebra formalism, which were developed by Burkhardt and Frenkel, etc. And there was also around the same time axioms which were written by Kontsevich. And so these axioms, these people were trying to set a firm basis for conformal field theory following the BPZ framework. So as I said, on one side you have these, these discrete path integrals. So this is one example. You have some kind of Hamiltonian H, and you look at observables of statistical physics systems, and you try to go to the scaling limit. And one other way to describe the scaling limit is by continuum path integrals. Okay, And what is a continuum path integral? It's, it's some kind of in math we call it a measure, but in physics they don't like the terminology measure. So it's a volume form on the space of functions on the surface. So I'll be working in 2 dimensions in all this talk. So I mean, lots of stuff is done in higher dimensions, of course, but I'll be talking about 2 dimensions. So I'll be talking about a surface. So these discrete statistical physics models, we expect them to be able to describe them also by continuum path integrals, which are volume forms on the space of functions on your surface, and which are sampled according to some kind of volume form, which would be the uniform volume form on the space of functions, this d phi, but reweighted by what is an action, which will be e to the minus s of phi. So s will be an action. And on the statistical physics side, you have natural observables, you have spins if you're looking at the Ising model, etc. And on the side of Feynman path integrals, you want to construct fields, so indexed by some set alpha, and then you want to compute correlation functions, so at different points in space-time, x1, xm, etc. Okay. So let me go to a bit to the topic of today. So let me start with, so as I said, I'm going to be really interested in Segal's axioms. So Segal wrote his axioms, I think, around 1990s or something. So he's in geometry. And so he wrote a manuscript around 1990, and he only published it, I think, in around 2004. And what does he say? He says, the manuscript that follows was written 15 years ago. I just wanted to justify my proposed definition by checking that all known examples of CFTs, so conformal field theories, did fit the definition. This test held me up, etc. So essentially what he's saying is that he wrote a certain number of axioms that a conformal field theory should satisfy, but the problem is he came short of non-trivial examples. And so that's why he delayed the publication. And well, what we kind of did along the past 6-7 years with my collaborators is that we had an object. So we constructed what is called Liouville conformal field theory using probability theory. And what we did recently is we showed that this probabilistic construction we have, it does satisfy Segal's axioms. So we have a completely non-trivial example of an object which is well defined mathematically and which satisfies Segal's axioms. And once we prove this, this leads quite naturally to proving that what we constructed satisfies, in fact, the conformal bootstrap formalism of Belavin-Polyakov-Zamolodchikov. So today's talk, it's roughly going to have, it's in 2 parts. One part is to, construct Liouville and using probability theory and stating at least that it satisfies Segal's axioms. Then in a second part, if I have more time, I'm going to show how the fact that Liouville satisfies Segal's axioms leads naturally to showing that the conformal field theory we constructed, this Liouville, satisfies the conformal bootstrap formalism. Okay, so let me start with Segal's axioms. So first, let me highlight the correspondence that's behind it. So take a disjoint union of parametrized circles. So take B independent circles, say, and to this, we look at the tensor product. So to each circle, we associate a Hilbert space. So that's what Segal did. So you take a circle and you associate a Hilbert space. So it's going to be, we're going to see it as it's going to be an L2 space. So we're going to put a volume form on some space M. And the Hilbert space is going to be the square integrable functions on this space. And if you have B circles, then you just take the tensor product. So you take B is the number of circles. So you just take B copies of M and you put the tensor product volume form on this space. Now, in fact, let me say what is M going to be. In fact, M is going to be the space of functions is going to be a space of functions on the circle. So when you have a circle, in fact, you take a function on the circle. Now, when you have a Riemann surface, you have with B circles as a, so we're going to parametrize our Riemann surface with circles using, geodesic boundary. So we're going to put a metric with geodesic boundary, and we're going to parametrize our Riemann surface by B circles. And what we're going to do is we're going to each Riemann surface with these circles on the boundary, we're going to associate what is called an amplitude. Okay, so an amplitude is just a function defined on m to the power b, and which is a square integrable. So the image you have to have is you have this Riemann surface which has b boundary circles, and to each circle, so to each function on the circle, on the boundary circles, you associate some number, which is the amplitude. Okay, and we're going to consider generalized, more general Riemann surfaces. We're going to put marked points. So we're going to put points like x. So x is going to represent x1, x2, xm. And to each point x on your Riemann surface, we're going to associate a weight alpha 1, alpha 2, alpha m. Okay, so this is what I wrote here, the marked points. So you should see this as an m tuple of points xi, and alpha is an m tuple of weights that we associate to each point. Okay, so once we've written, it's important to have the definition in mind. So
I have a question.
Yeah.
So M is in general an infinite dimensional space, right?
Who?
M is in general an infinite dimensional space.
M is the space of functions on your circle, so it's an infinite dimensional space.
Yeah. Okay.
So you have your circle, and you look at all functions roughly defined on the circle. So it's a Fourier series. It's sum of alpha of phi n e to the I n theta. So they're going to be real value. Yeah, it's an infinite dimensional space, and that's what makes things difficult. In fact, that's why we had to sweat a lot in all our theories, because most of the results we needed were not available in the literature. Okay, so yeah, so you take a function, a different function on each circle, which is a boundary of your Riemann surface, and so you have your functions phi 1 to the phi b, and an amplitude is a function of these phi 1, phi b. So it's a function whose variables are functions themselves.
It's a functional in that sense. In the physics we call it functionals.
Okay, functionals.
Yeah.
Okay, so so as I said, if you're interested, I did lots of drawings in this IAS talk. So really, I think it could be clearer. So okay, so this is what Segal introduced. He introduced these things, these amplitudes. Of course, okay, let me say one thing. What is important here, if b is 0, because you're allowed to take b equals 0 here to you. If b is 0, this means the Riemann surface, okay, it has no boundary, and it just has marked points x1, xm with weights. And in that case, the amplitude, well, it's just a number, okay. It's just a number, and it's not a function because there's no boundaries. And in that case, it's the correlation function. And at the end, what you want to do is you want to compute the correlation functions, which are these amplitudes with no boundary, which are just a number. And that's why upstairs I wrote, if there's no boundary, you associate a complex number. This is the correlation function. Okay, and so he had this formalism, and he said, okay, now we're going to suppose that these amplitudes they glue properties. And if we can construct such a system, then we have a conformal field theory. Now, what are the rules? First, there's geometric rules, and then second, there's a gluing rule. So the geometric rules are the following. If you have a surface sigma with a metric G, with marked points x1, xm, with weights alpha 1, alpha m for m an integer, if you take a diffeomorphism and you look at the amplitude where you pushed your Riemann surface in the natural way, I mean, you look at the image of sigma by psi, you push the metric G by psi, so this is the push forward of the metric G. You move the points x according to psi, of course, so you send them, and you look with the same weights alpha 1, alpha m, then you get the same thing. So you have diffeomorphism invariance of your theory. The second thing you want is the Veil covariance, meaning that if you look at an amplitude and you change your metric with respect to a conformal factor e to the omega, then you get the same object times two terms. Now the first term is exponential some constant times what is called the Liouville action. This is also called the Liouville action. So times this action here. So the function, you take the gradient square plus 2 times. So this is the kj is the Ricci scalar curvature of your metric. And you integrate against the volume on your surface. And you get this term in front, and you also get a product e to the minus some weights, the function omega, evaluated at the marked points. Okay, and so in this, so you want your system to have this property, and where so here CL is called the central charge, and the delta alphas, okay, the weights which depend on alpha, are called the conformal weight, okay, of the alpha. So remember, behind this behind these amplitudes, these alphas, they represent fields that and x is the point where you evaluate these fields. So for those who are not that familiar with conformal field theory, I mean, this is very natural assumption. So let's say you have a surface with no marked points. So x is empty, there's no marked points. So this term here becomes 1, doesn't exist. And this rule is the one you see, for instance, when you associate to your surface the determinant of the Laplacian. Okay, I mean, conformal field theories, they react like the determinant of the Laplacian. So actually, this is what you should have in mind in some sense. So you see, this is rather natural. What is it saying? It's saying that if you look at the amplitude, it's saying that it's a function on moduli space, because it's D-field invariant, and if you rescale your factor, your metric, well, you get essentially the same thing. So it's saying that you're constructing an object which lives on the moduli space of Riemann surfaces with marked points. So it's very natural from a geometrical point of view. Okay, so these are the two geometric rules that you have to impose, and now you have the gluing rule, which is very, very important. And for those who do for those who do probability theory, this is a very beautiful axiom, because it's the natural generalization to Riemann surfaces of what is called the Kolmogorov-Chapman equation in probability theory. For those who know what a Markov process is, this is just saying that Segal's axioms, it's a Riemann surface analog of what is a Markov process in probability theory. And it says the following. So if I have my surface sigma 1 on the left with, so here I have 3 boundaries and I have 1 marked point, and I glue it to a surface sigma 2 on the right. So by identifying 2 boundaries, so it has a marked point x2, then what is the amplitude associated to this surface that I've glued? Well, I just take the field on this side equal to this one, and I integrate with respect to mu0. So I take the trace of the tensor product of these two amplitudes. And this gives me the amplitude on the new Riemann surface where I've glued. Okay, so trace of IG means that so remember, I have a field on each circle. So I take the same field on these two circles and I integrate with respect to the background measure volume form that I've put in here, mu0. So I contract two variables, okay, in my system. And then I end up with a function which depends on a function here, a function here. So it depends on 4 boundary functions now. And I've contracted 2. And so the gluing rule is really that to construct the amplitude associated to this Riemann surface, I use this contraction principle.
So in general, you take not only similar functions on the gluing surfaces, but you also sum over the functions, right? Or over the function space. Right?
Yeah, so yeah, exactly. So what this trace means is, if I want, so the amplitude of this Riemann surface where I've glued, it depends on 4 variables, right? It depends on here, this one, and this one. And so what we do is we sum, we take the functions here and we sum on all functions on this circle.
Yeah, that's
that's the trace IG. We take the same function here and we sum. Okay, yeah, and so it means that we lose 2 variables, right? We sum on we're summing like on intermediate states. It's very natural. Okay, and it essentially tells you that you have some kind of it's called some kind of Kolmogorov-Chapman equation. So it's kind of funny because if you look at these 2 axioms, you could say, okay, well, okay, let's construct these, but that's what Segal says, that it's not easy to construct non-trivial examples of this. Okay. Yeah, so here I'm being a bit so here I'm making a bit concrete what I said. So I kind of cheated. I said that M is the space of functions, but mathematically speaking, things are a bit more complicated. It's a space of functions, but in a generalized sense. So what is this thing? It's that you take, so H, the Hilbert space, it's the space of functions, but so remember I'm on a circle, so I can always Fourier expand my circle, my function. And in fact, where are these, what is going to be my space of functions? It's going to be in a generalized sense. I mean, I'm going to take epsilon positive. Usually it's something that happens often in conformal field theory or quantum field theory, is that the objects, the fields that you have, they live in a generalized space. And they're functions in a generalized sense. They're not really real value. So I'm going to take the space of Fourier series, but I'm going to suppose that the sum of the Fourier coefficient squared, time this term, which is going to 0, is finite. Okay, so I'm not quite in L2. I'm not quite. This is not quite a function, and I'm going to put some kind of volume form on this space of functions, which is going to be essentially the Gaussian free field. Actually, it's going to be a form of the Gaussian. And so let me explain why. And the heuristic behind Segal was to view amplitudes by the Fineman path integral description. So essentially, what he had in mind, and this is what we're going to implement, is that the amplitudes, on your surface with your metric, your points xi, your weights alpha I, is the integral on, say, the space of all functions defined on your surface, which have boundary value these phi i's. So I have my functions, associated to each circle. Now I'm going to sum over all functions in the surface whose boundary values are given by these boundary functions. And I integrate according to some kind of volume form, which is a Fineman path integral, and I evaluate under this, fields at the points at the marked points x1, xm, and with weights alpha 1, alpha m, etc. So here I indicate that I'm integrating over all functions defined on the surface with boundary value given by these boundary functions. And when I don't have any boundary, as I said, I'm just looking at the correlation function on my surface. So this is really what you have. This is what I think, Segal had in mind when he did his axioms. He had this path integral description in mind. And with this, it's not very difficult, kind of to heuristically derive his gluing axiom, that if you assume that the action is local, so an action is local if it's it's the sum of your field and you look at observables around the point where you integrate, then what you have is that if you cut your surface into two, say, along some separating cycle, then the action it can be written naturally as a sum. And then if you condition, say, your field on, so this is a genus 2 surface, and say you want to integrate over all functions, you can first, disintegrate your functional measure d phi here by saying, I'm first going to prescribe the value of phi on my separating cycle, and then I'm going to disintegrate my measure. And if you think of things this way, you kind of naturally end up with this thing will be necessarily factorized into two terms, and one so you disintegrate with respect to the value of your field on the separating circle, and then you prescribe the value on the left and the right to being equal to the value here, and this naturally leads to the idea of the gluing axiom. So, okay, the thing you have to have in mind is that just by if you have a Feynman path integral description of your system in mind, and you cut naturally your action in two pieces by conditioning on the value of your field on a separating cycle, you naturally are led to saying that your system should satisfy this gluing axiom that Segal wrote. Okay, so this is so I'm kind of done with this general overview of what Segal is and how you should think of this.
Just a small clarification.
Yeah.
So on the right hand side, you seem to only have x1 alpha 1, x2 alpha 2, whereas on the left hand side you have up to xm. What is there's something going wrong? I mean.
No, okay, I'm sorry. Yeah, okay. Let me explain okay, this is not a very good notation. So okay, if I have okay, when I cut it along this cycle, right? So in fact, I'm going to, so okay, what I call x1 here and x2 here, it's in fact it's a collection of xi's.
Correct.
Okay.
So it should rather be xi1 and xj2 or something like that.
Yeah, I mean, you take all the xi's which are on the left, you put them in this amplitude.
Yeah.
You put all the xi's which are on the right, and you put it in this amplitude. So x1 is kind of, okay, it's because sometimes I called x1 xm, I called it, bold x. Okay, see here, this is kind of a bold x. This means x1 xm, okay? And,
okay, that's clear.
And so this is a bold x1. Okay. It means all the xi's which are on the left. And of course, and alpha 1 it's the weights associated. Yeah, of course, I hope this notation, yeah, maybe. Okay, and okay, so now, okay, take-home message is that you write natural assumptions to construct the function on moduli space, which has this gluing property. And behind this, you have some kind of heuristic, which is quite natural if you have a path integral description of your system, of your conformal field theory. So it's a very geometric way of thinking. And so now the point is that in 2014 with I was with Rémi Rod, Antti Kuppinen, and there was François David. we had this path integral, which is in physics, and which was supposed to describe a conformal field theory. And so the first thing we did kind of is, well, can we construct this path integral? And then the answer is yes. So what is this path integral? So this was introduced by Polyakov in 1981 in his paper, Quantum Geometry of Bosonic Strings. So you take a Riemann surface with a metric G, and you want to look at this volume form on the space of functions on your surface. So you reweight what is called the free field by the exponential minus what is called the Liouville action. And what is this Liouville action? You reweight by, you integrate on your surface the gradient square. So this is the free field term, the Gaussian free field term, plus Q times Ricci scalar curvature times phi, plus the interesting term, which is the interaction term, plus mu to the e to the gamma phi, integrated against the background volume form on your surface. So this thing, which was introduced by Polyakov, okay, we're going to define it for gamma in the range 0, 2, and Q is going to be related to gamma via this special relation, 2 over gamma plus gamma over 2. And we're going to take mu positive. So the Liouville theory depends on 2 parameters, gamma and mu is not a very important parameter. It has to be positive, but essentially you can take mu equal 1, and the theory I mean, they're all equivalent, in fact, for different mu's. Okay, and why is this action quite natural? I'm not going to have to go into too many details, but it's because if you take the minimizer of this thing, you're solving Laplacian phi equals e to the phi, right? Exponential to the phi. And so the minimum of this thing is gives you constant curvature metrics on your surface, negative curvature. So it's kind of, that's why it's seen as kind of the natural random theory of Riemann surfaces. Okay, so this thing, so I'm specifying, my general discussion to Liouville. So in this physics heuristics, we're going to take this action. And so we're going to look at the Hilbert spaces, as I said, the space of trigonometric series. And so when I have a trigonometric series, I can expand it. So in Fourier, I'm going to distinguish the 0 mode, the average of the field on the circle, and the higher order of Fourier modes. So my Hilbert space is a space of generalized functions, but so they're going to be real valued. So I can always write real valued functions under this form. And I'm going to write phi n as xn plus yn over square root of n. There's a 2 also. And I'm going to equip this space of functions with a volume form. And the volume form is going to be the following. I'm going to sample my xn, yn as standard Gaussian variables, all independent. So this is my measure P. And I'm going to sample my 0 mode according to the Lebesgue measure. So it's the only translation invariant measure there is on the real line. And my Hilbert space, so as I said, so this is this big M, it's the space. So one can show that if you do that with probability 1, I mean, with full mu0 measure, this object lives in any h minus epsilon on the circle. And so the Hilbert space is the space of functions equipped with this volume form, DC tensor P. So this is in fact the Gaussian free field on the circle. Okay, so now I have a Hilbert space. And now I have to construct my amplitudes. So I have to construct my path integral. So how do I do? So I have here's what I do if I have a Gaussian free field on a surface sigma with boundary. Okay, so I take a surface sigma with boundary with a metric G, and So this is a way of constructing the Gaussian free field with Dirichlet boundary conditions. So I take a sequence of ID standard Gaussians, alpha n. I solve the Laplacian. So it has eigenvectors and eigenvalues. So I solve the Laplacian with I look at the orthonormal basis of eigenfunctions of the Laplacian with Dirichlet boundary conditions. And so I construct this infinite series out of it. So these are the lambda n's are the eigenvalues and the en's are the eigenvectors. So, okay, for normalization purposes, I multiply by square root of 2 pi. And if I do that, I get this random series defined on my Riemann surface. And you can compute the covariance, and it's going to be the green function of the Laplacian. So, you know, I have a Laplacian, and I can invert it by a kernel, which is called the green function, which has a logarithmic singularity on the diagonal, okay? And so if I want to define my path integral, the first thing I do, in fact, is I define the Gaussian part of it. I take mu equals 0, essentially, in my path integral. And then I'll explain how I go to positive mu. So let me first define the path integral. If mu equals 0, and say curvature, we don't take the curvature term. So now I say that this volume form on the space of functions with boundary value given by these functions defined on the boundary circles, it's nothing but, okay, up to some determinant of Laplacian, it's the average of the Gaussian free field with Dirichlet boundary conditions plus the harmonic extension of the boundary functions. So when I write e to the var phi here, this means that I fix, remember, I fix my functions on the boundary and I integrate over the Dirichlet Gaussian free field. And so, and the field that we're interested in, it's this Dirichlet boundary condition free field plus the harmonic extension of these fields on the boundary. So this thing solves Laplacian is 0, and on the boundary, it's equal to these phi i's I have. So this is the clean probabilistic definition of this infinite dimensional measure on the space of functions, or dimensional one. Now that I'm equipped with this definition, I can try to define what is the amplitude for the Liouville action. So see, the Liouville action, it has two extra terms. It has some kind of curvature term, remember, and it has an interaction term, okay? So I've only defined things in a clean probabilistic way for Q, say Q equals 0 here, and mu equals 0. So what I do is I split my Liouville action in two. And so I say that I gather the gradient squared term part here. I push it with the d phi. And so I have a definition. And then I treat the two other terms here and here as a Radon-Nikodym derivative with respect to the Gaussian free field measure that I have here. And so this leads to the following definition. For my amplitude, say, so let's say with a boundary. So fix, sorry, okay, I usually put xm here, so okay. This is x1 xm, not n. I mean, because I since the beginning I've been talking about x1 xm. But okay, never mind. Anyways, n is a natural number. So I have my x1 xm's, yeah. My points on my surface, I have my weights, so alpha 1, alpha m, and I'm going to suppose that they're real and less than this capital Q I have. So gamma over 2 plus 2 over gamma. Now, the amplitude, the definition is going to be, I take the so the fields in Liouville are going to be the exponential of alpha, the field. So these are my V alphas of xj's. So I look at, so I average over my, so remember, my field is the Dirichlet Gaussian free field plus harmonic extension of the boundary values. So by definition, the amplitude is going to be some kind of geometric flavor function of the boundary values. So this is kind of completely deterministic. the average of, so the product of my E alpha A's phi of xj's, okay? Yeah, sorry. And now I'm going to take the two pieces that are in the Liouville action and I'm going to see them as a Radon-Nikodym derivative with respect to this Gaussian free field measure. So I'm going to take the average of e to the minus 1 over 4 pi q, so Ricci scalar curvature times the field, plus mu exponential gamma the field that I integrate over my volume form dVg. Now, here is where probability enters the game. Is that you see this field here, as I said, it has a very smooth part. Okay, harmonic P is for harmonic extension. This is very smooth in my surface. Okay, it's a harmonic function. So, and it's actually completely deterministic. Okay, but then I'm averaging over this Dirichlet Gaussian free field, which is in here, hidden, and it's also upstairs here and also here by the decomposition. The problem is the covariance function of this field is the green function, and we know that at coinciding points, it's infinity, right? Because the green function on a surface when 2 points collide, it's like log over 1 over the distance of the 2 points, and so it's not.
A question.
Yeah.
When you are saying that you're averaging over the xg's, what are the weights that you're taking for the average?
The what?
What are the weights for the average?
Weights.
Yeah.
No, there's no weight here. It's a definition. It's when I say an average, it's this definition here. It's you see, I have a definition, right? This is it's a probability measure here. Expectation of I mean, okay, when I say an average, okay, the theorem is there exists something which depends on points and on the surface x and on randomness that we call omega usually, and there exists a probability measure, meaning that you know that gives total mass 1 to my space. So meaning that here, if I put 1, take capital F here equal 1, this is 1. So there exists a probability measure such that, and a random Gaussian field on it, whose covariance is given by the green function. It's an abstract theorem if you want. Okay.
Now, in general, when you define the correlator, for instance, a GGXX prime, it's just in normal field, quantum field theory, there's no such notion of an average. So I was just wondering.
When I call an average, I mean you average E is called, what I call the average is E here. Okay, I average on all randomness, and I look at the correlation of my Gaussian free field at 2 different points, and I get the green function.
So by averaging, I suppose you mean that you take xgx prime in some path integral. I mean, you insert these 2 operators in some path integral.
No. What I mean average? No. I say that if you have, okay, this thing is defined in the space, a negative Sobolev space. What I'm saying is that with I can construct a Gaussian field on my surface, a Gaussian free field. It's called. It's a generalized function on my surface. So that I sample with probability 1. I don't insert anything here. What I call an average is when I say average on xg, it means that I have a probability measure on a space.
No, for instance, in that specific expression, on the right hand side, you have this average over this f of x g plus p phi, and on the left hand side, you just have, instead of xg plus p phi, you just have capital phi, and you have this measure.
This one.
Yeah, you're that's supposed to be like a weight for this particular kind of.
Yeah, if you want, when you say that the weight, okay, this is a crucial point. When you do quantum field theory and you're a probabilist, okay, and even if you're not, in fact, it's always this. You you don't know what d phi is. The uniform measure on the space of functions, there's never going to be a mathematical definition of this. However, you can interpret, if you put this gradient square term, then, okay, I shouldn't put an equal here. I should put a 2-point equal. This is a definition. It means that we have a probabilistic theory. This is not new. This is old, like 50 years more, even more. On the right, it's the probabilistic definition of what this object is on the left. I mean, a physicist, he would kind of, he would play around with this thing. But what is great in probability is that we have a clean mathematical definition of what this object is. So if you want, when I say average on this, it's kind of, okay, I'm taking the uniform functions and I'm reweighting by this. The problem is, if I say that, someone in math is going to say, okay, but do you have a definition of this? And the answer is yes, it's the Gaussian free field. It is the unique probability measure, which, in each point of space of your surface assigns a Gaussian variable, and the covariance between between these variables at two different points, it's the green function. This uniquely determines a random function on your surface, and it's called the Gaussian free field. And this was a construction you can make out of it. This is a way of constructing.
Yeah, for instance, if you just take, instead of f, you just take xg for the function capital F. If you just take xg x prime, then you would get precisely what you get in quantum field theory, because on the left hand side you would just have f of xg x prime.
If you take what you say, you're going to get you're going to get the 2-point correlation function.
Yeah, that's what I'm saying. I mean, on the right,
so you'll get the green function. Yeah.
On the right hand side, you just have the on-shell values of the capital phi, which is what you get after you integrate over the path integral. I mean, when you integrate in the path integral sense.
Essentially, this is a very general definition. Then you you plug in this definition what you want for capital phi, for capital F, And in fact, if you're interested in Liouville, what is the natural observables? It's not the field itself, but it's exponential of the field, because it's a theory of random surfaces, and this phi should be seen as a how do you call it, as a random conformal factor. So okay, I have this definition, so I plug in the Liouville part, so the curvature term. So I take, for a capital F, I take e to the minus curvature plus interaction plus times product of these exponential at different points. Okay, I just plug it in this definition to get my amplitudes for Liouville, and I get this guy here. And so this is if the surface has a boundary. If it has a boundary, then there's no harmonic extension term. Okay, it's just the Gaussian free field with, say, average 0 on your surface plus a 0 mode term.
Vincent, quick question.
Yeah.
So what is special about this restriction on this Liouville coupling constant gamma to be between 0 and 2?
Okay, so this is exactly this. So of course, okay, you could, so the restriction comes from here. So you see, I have a Gaussian free field plus a harmonic extension, okay? So I want to define e to the gamma, the Gaussian free field. And this is where probability is restricted. It's because this makes no sense because of the ultraviolet divergence in the green function. The function, you see, I have to make sense of e to the gamma Gaussian free field, okay, times my volume form on my surface. So this is not defined pointwise because the covariance is the green function. So it's only defined in a generalized sense. So I have to Vic order this term. So what I do is, if I want to define this, well, I introduce a cutoff scale, ultraviolet cutoff scale epsilon. I smooth my field at scale epsilon, and I have to add a counter term for this thing to converge. And what I do is I add the counter term epsilon to the power gamma squared over 2. And if you do that, you can actually show that when the ultraviolet scale epsilon goes to 0, this thing converges to a volume form on your Riemann surface. It converges, and the point is, so it's a random. So each time so behind this I have an average. Okay, this expectation is an average. So each time I toss a randomness, I get this generalized function. I smooth it, and it converges, and it gives you a volume form in the limit. And the interaction term is the total mass of this volume form. So this term is easy to define, but this one is complicated, renormalization. And here's where the restriction comes from. It's because you can show that this always converges, but it converges to the trivial volume form on my surface, 0, if gamma is outside this range. If gamma is bigger or equal to 2, what Kahan showed, actually in 1985, is that this converges to 0. And so it kills this renormalization procedure kills the volume form. And so you're constructing Gaussian free field theory. You're not constructing Liouville field theory. And so it's because of this probabilistic theorem to define the exponential of my field that I have that the probabilistic entry of the field is restricted to this, to Liouville field theory is restricted to this value gamma. And it's also restricted, you need real weights here, alpha 1, alpha m, because in physics, I mean, you can look at these correlation functions for complex alpha i's, complex gammas, etc. But in probability theory, you know, we like positive quantities, etc. And we have this probabilistic theorem. And so our entrance window is actually, you know, restricted to values of the parameter. Okay.
Why are the phi's in the exponent? Phi xj's in the exponent? Because I suppose they initially they were supposed to be in the, I mean, in the original expression they were supposed to be like the correlate. You're talking about the correlators of the phi. So here, are you exponentiating them so that you get some sort of a generating functional or something?
Yeah, this is I insert these e to the alpha phi, and so what I also hid under the rug is that this is not defined pointwise, right? Because I told you the Gaussian free field, it lives in a negative index Sobolev space. So in fact, if I want to define this properly using probability theory, I also have to renormalize each of these guys with an ultraviolet scale cutoff, and I have to compensate with a same kind of procedures here. You know, I have to take epsilon to the alpha j square over 2 times e to the alpha j phi epsilon and go to the limit. And okay, we're able to do that. And at the end, we get a clean probabilistic expression for this thing here. And for the correlations. So in fact, it's kind of funny because I won't have time to show you, but for correlation functions, the amplitudes, etc., we have a completely, we have a probabilistic expression just in terms of the exponential of the Gaussian free field. So these Gaussian multiplicative chaos volume forms. Okay, and so here's this theorem I state with Guillermo, Kupienen, and Remy. Now, I constructed amplitudes as soon as I have weights alpha 1, alpha m smaller than q. And the theorem is that, okay, I consider the amplitudes with this extra condition. So this condition ensures that these things are in the proper L2 space. So I look at all the amplitudes such that alpha I are smaller than q, and the sum of the weights is bigger than the Euler characteristic of the surface times this capital Q. So capital Q, remember, it's gamma over 2 plus 2 over gamma. Then our amplitudes satisfy the Segal's axioms. So we can show that this thing that we obtain using probability theory glues in the proper manner, in the right way. Okay, so I have two minutes left, right? Is that correct?
So, I mean, since there were questions in the middle, feel free to take, 10 minutes or so.
Yeah, maybe. Oh, okay. So, I mean, let me just pause 1 minute. I mean, if people are interested, as I said, we had much more time in IS, and so really, if you're interested, you go to the IS webpage, or I could send maybe the link, and it's exactly the same talk, but we had a bit more time, so I think some things can, if you have questions, I think maybe some things will be more clear. But also another thing that I like to say is that, okay, if there's no boundary, then you get the correlation functions, as I said, which is the thing you really want to compute. And we have, nice and new probabilistic expressions for these objects, which were not known in physics. So I mean, okay, it can be of interest to some of you. Now, okay, so now I have this now I have my definitions, etc. They satisfy Segal, so we're really happy. But so now the question is, okay, can we recover the bootstrap? Because I think that if I know actually that, because I've talked to dozens of physicists for the past 5-6 years, and when I ask them what is Liouville, they tell me, okay, well, it's some 3-point function called the DOZZ formula. I integrate it against conformal blocks, etc. So it's, I mean, a priori, this bootstrap construction, which was done by, in fact, Dorn-Otto-Zamolodchikov and Zamolodchikov in the mid-90s, a priori, it looks very distant from these objects that we've constructed. And so let me try to say now, I'll give a description of the bootstrap. Now, in physics, what, based on these axioms, actually, like Segal kind of axioms, the bootstrap construction of this theory is based on giving the 3-point correlation function. So, by playing around with Möbius transforms and the conformal invariance of your system, computing the 3-point correlation functions, it amounts to computing them so it weights alpha 1, alpha 2, alpha 3, these exponential alpha i's of the field at 0, 1, infinity. With a Möbius, you can always send 3 points to 0, 1, infinity, and up to trivial terms, the 3-point correlation function, it's nothing but the same thing as the 3-point correlation function when the points are set to 0, 1, infinity. And in physics, the construction is based on the DOZZ formula. They postulate some kind of crazy formula for the 3-point correlation functions that they're going to inject in the bootstrap to construct higher order. This is and so it was guessed, or postulated by Dorn-Otto-Zamolodchikov-Zamolodchikov in the mid-90s. And so the first theorem I want to highlight in our program of relating our probabilistic construction to the bootstrap construction is that we have our probabilistic expression for the 3-point correlation functions, and it matches. So this is what we proved with Antti Kupienen and Remi Rod in 2017. It actually, our probabilistic expression matches the exact expression which was derived by these people. So you see, I'm not going to enter the details, but you have lots of special functions. There's some kind of crazy function for the 3-point function. And it took us actually a few years to show that on one side, so we have a probabilistic expression and it matches this. So, one should see this theorem as a mapping between the Gaussian free field and this formula, this DOZZ formula. So that's the first theorem. And then if you want to, connect, so I'm going to finish with kind of a theorem we proved. Now, if you want to connect our work with the bootstrap, you have to introduce what are called plumbing coordinates. So remember, the correlation functions of Liouville, well, they satisfy these axioms, these Gavitsky axioms or Segal axiom. And so they're functions on moduli space. So it's natural to, in fact, in conformal field theory, introduce coordinates which are analytic, holomorphic on moduli space, because you expect that your correlation functions are expressed in terms of holomorphic functions. So what is these plumbing coordinates I want to introduce? So you take a pan decomposition of your surface, and you can glue cylinders inside these separating cycles. And so when you glue a cylinder, the cylinder has a length, and you can glue by twisting also the cylinder. So it's really a function of Q, which is a complex parameter, because it has a length and an angle. So Q is a complex variable, and this by using these gluing of cylinders, which have a length and that you can twist, you can construct a local coordinates on moduli space. So on the moduli space of surfaces of genus H, so H is the genus of my surface, and M is the number of mark points. And this procedure, it provides holomorphic local coordinates on your moduli space. And okay, the theorem we proved recently, and I'm going to finish with this thing, is that, okay, if I look at my correlation functions with my mark points, etc., I can actually use my plumbing coordinates. So I'm going to get a new surface with, in fact, a metric which is going to depend on Q. Well, I can decompose my correlation functions as an integral on the dimension. So this is the dimension of moduli space, right? It's 3 times the genus of my surface minus 3 plus the number of mark points. I can write my correlation functions as an integral of, so here I integrate on dp. So this is just Lebesgue measure, dp1, dp2. And I get the product of 2 terms. So I'm going to get a product of these DOZZ terms that I talked about. So the 3-point correlation functions, and these depend on the model. And I'm going to integrate also against a family of holomorphic functions, holomorphic in the plumbing coordinates, to the square. So I get, and so these are the so-called conformal blocks of conformal field theory. So they depend on my integration variables pi. They depend on the conformal weights of alpha 1, alpha m, right? And they depend on the central charge of Liouville. By the way, the central charge of Liouville is 1 plus 6q squared. We actually know this explicitly. And we also have expressions for the weights in Liouville. And so what I want to end by saying is that I won't go into the details, I don't have time, but using, the fact that our correlations, we can cut them into pants and say that the gluing of these amplitudes, at La Segal, we can naturally decompose our surface along these plumbing coordinates, and we naturally can recover that the correlations should satisfy this bootstrap formulas. Okay, so I'm going to end here. So because I'm ending on a, I'd say the latest statement proof that we've done in this field. Okay, I'm done. Thank you.
Thank you.
Please ask questions. I mean, even very general or okay.
Yeah. So let's thank the speaker first, and then people who have questions. So actually, I have a couple of questions. So when you say that you can sort of derive the DOZZ thing, I want to sort of understand better how to think about it in probability theory. So the derivation that I sort of know is due to Teschner, where there's a trick that you can do by replacing one of these external insertions by what in physics we call degenerate fields, and that imposes some constraints on the 3-point. Like you take a 4-point function, make one of the fields degenerate, that imposes some constraints on the 3-point function, some functional equation, you try to solve it and so on. So is that kind of thing
okay,
happening under the hood?
Yeah, so of course it's exactly so. I there's so many people who have done so many stuff, interesting stuff, and of course Teschner is, I should emphasize that Teschner was a great a source of inspiration for us because it's actually what you say. So we have a probabilistic expression. So in fact, it's a very simple probabilistic expression. It's the average of some random variable, okay, with respect to Gaussian Free Field. And what we do is that we show that our correlation functions, they satisfy the axioms that Teschner needs to derive. So we look at the correlation function with 4 points, we insert a degenerate one, and we show that it satisfies BPZ. And then we play around with asymptotic expansions, and we are able to implement Teschner's trick. And it's actually very nice because a very important part of the work is to show that we can recover the Liouville reflection coefficient. And what we discovered is that the Liouville reflection coefficient, it's just the constant in front of the tail expansion of these Gaussian multiplicative chaos measures. So the take-home message is that, yes, we show that our probabilistic expression satisfies what is needed to implement Teschner's trick.
I see.
Because Teschner is kind of a set of axioms. He says, okay, imagine you have a degenerate field that it satisfies BPZ. Imagine you have, you have these expansions when points collide. Then at the end, it enforces the 3-point to be equal to that. So we show that each step of Teschner's axioms are in fact satisfied by our correlation functions.
Okay. Yeah, I think Pranav has a question.
Yeah. Hi, Vincent. Thanks for a great talk. I just wanted to ask how much of this story can be extended to TODA theories, and what are some of the challenges in that path?
So we have defined TODA theories recently. It's a paper we did with Riemann and Baptiste Cercle. So what we did is we defined TODA conformal field theory, no problem. We have a generalization of all this story, and quite recently he's finishing the paper as I speak for TODA theories where there are two fields, so SL3. So Baptiste, who is a student of mine, and Colin Guillermo, he proved the Fateyev-Litvinov formula. So this extension of the DOZZ formula for TODA. This he has managed to recover with our probabilistic expression for the correlation function. Now, what are the challenges in TODA? Can we derive a general 3-point correlation function? Because there's no such thing in TODA as DOZZ formula. You only have a DOZZ formula for special weights, alpha 1, alpha 2, alpha 2. So what our construction provides a clean definition of the 3-point correlation functions, which is not in physics because there's no exact formula for all weights. So there are two challenges. First, try to recover a general formula for the 3-point correlation functions in TODA. And second, try to understand the 4-point, the 5-point, etc. correlation function from the perspective of the bootstrap. And so for that, there's a difficulty is that there's no really such thing as a definition of a conformal block in physics, as far as I understand.
Mm-hmm.
Because you have different algebras acting and they don't enhance your full space. So we're trying to kind of understand what kind of notion of conformal block we can derive out of all this.
Mm-hmm.
So we're doing scattering theory on TODA right now.
I see. Thanks.
I mean, there's lots of challenges. We're also constructing the sine hyperbolic model and all these models. I mean, so these are the affine TODA theories, which are not conformally invariant.
Mm-hmm.
So I mean, our program is kind of Liouville's nearly done. I mean, we kind of understand all the aspects now. I mean, but now we're trying to extend this to affine TODA theories. So the ones that are conformally invariant and the ones that are not.
Mm-hmm. Yeah, that was going to be one of my other questions, is like how much of this is specific to conformal theories as opposed to more general. I mean, quantum field theories? Like, can these probabilistic methods be used to understand?
You want to know how much we can extend this stuff to other things?
Yeah.
Well, the problem is it's summarized here. I mean, Liouville is a special action, right? I mean, see, so I wrote the Liouville action here. Yeah. So I mean, this thing is so Liouville. The problem is, if you want a conformal field theory, if you don't put the exponential interaction here, well, it's very difficult out of the path integral to construct something which is going to be conformally invariant. So there are conjectures, but you know, you can put polynomials here, but since they're not conformally invariant objects, you need to rescale them, and there are lots of conjectures on taking scaling limits on path integrals to construct things. But one thing's for sure is that you won't, here we actually, the construction of the path integral is not all that difficult. I mean, once you put all the ingredients together, but if you want to put another interaction, you need to do extra rescalings. And so right now, I don't see some kind of hope in the near future that probabilists are going to construct other conformal field theories of the Liouville using, or TODA, you know, exponential interactions, using probabilistic constructions of path integrals. Yeah.
Great, thank you.
I think we have a question from Shomudatta.
Yeah, could you go back, go to your page where you wrote the general expression for the correlators, in terms of the most general expression that you had for the correlators?
I never wrote the correlators. In fact,
No,
I wrote
in terms of yeah, this one, yeah.
Yeah, and so I never really gave the exact expression for the correlators. Let me just see.
No, I'm talking about this expression.
Okay.
So here, if you didn't have the Q and the mu gamma terms, then I understand that the expression that you would have is e to the alpha j phi xj. Now, in presence of the terms, in the presence of those terms in the action,
yeah,
you would the entire equation of motion will change, right? I mean, so you wouldn't have.
Oh yeah, the equation of motions, they change, yeah, because this is like inserting Dirac masses, right, in your integral.
No, what I'm saying is, in that case, capital phi would no longer be expressible as simply as xj plus p phi as you had before, because the equation of motion for phi itself will change and it will give rise to much more complicated behavior, right?
So I mean,
so
if you take q equals 0 and mu equals 0, that's what you're saying, right?
No. If you take q equals 0, mu equals 0, then it's okay. Then phi can indeed be expressed as xg plus p phi. Yeah. But if you have finite q and mu, then the very Liouville action, the action in the path integral, that itself will change. So if that changes, that means that when you're evaluating on shell, you have to solve for the equations of motion coming from that specific action and not just the free action. Getting my point?
Yeah, but okay, my point is that, okay, my point, I know, but my point is that we all map everything on computing things on the Gaussian free field, okay? This is, okay. Take f of capital phi here, okay? This is the definition of integrating with respect to the Liouville action, okay? It's integrating with respect to the Gaussian free field and reweighting space by this term. This term is a random variable with respect to the Gaussian free field. This is a definition of what is the Liouville action in probability theory. That's my, I see what your problem is. You're saying that, okay, Liouville is not just Gaussian free field. That's what you're saying, right?
Yeah.
Yeah, but Liouville is nearly Gaussian free field. If I take a function of the Liouville field, I put a function of my Liouville field here. So here it's the correlations. And I just reweight with respect to this term. What I'm saying is that Liouville action is Gaussian free field action reweighted by this term. And I see this as a random variable, a Radon-Nikodym derivative. So this, so you're done if you can make sense of this as a proper function of the Gaussian free field. And that's what we do. You integrate the Gaussian free field. That's no problem here, and you integrate the exponential, and this is done using a theorem by Kahan. I mean, you should really see, I understand, I think, okay, maybe I was not clear, but
No.
Essentially, things are not that complicated in Liouville because it's just reweighting by this term, the Gaussian free field.
So would this step work more or less the same way for TODA, or?
Yeah, it's the same thing in TODA. It's the same thing. We have in TODA we have lots of correlated. So we have Gaussian free fields who are correlated according to the Cartan matrix. Okay, right. And so you have lots of them here, and then you're basically done. I mean, you just put a sum here, and you take expectation with respect to correlated Gaussian free fields.
And you mentioned an idea, a sum derivative. I'm not familiar with it. Can you mention the names again?
For what?
You interpreted the extra terms as some particular derivative, Radon.
The Radon-Nikodym derivative. Yeah. Okay, Radon-Nikodym derivative. It's the term in math to say that you reweight by something. Okay.
I see. Okay.
So it's just saying that Liouville. I mean, what is very important is to understand is that all these things with interaction terms, we see them as random variables, these interaction terms with respect to the Gaussian free field measure. So we map everything on computing stuff on the Gaussian free field. Mm-hmm. So we really have a mapping of all these objects to functions, so complicated sometimes. I mean, these exponentials are complicated, but nonetheless, we map everything as functions of the Gaussian free field.
Okay.
Yeah, so my related question is, if you started off with the Liouville action and the e to the alpha j phi j in the action, along with just the Liouville action, that is the Gaussian term, along with the potential terms, yeah. Can you go from there to this expression? Is there a way of deriving this expression starting from there? Because unless you do that, this is just a conjecture, right? I mean,
what is a conjecture?
The fact that you're saying that when you take the Liouville action completely, the phi xj's will just be weighted by this extra term, and there would be no other extra thing going on. Because first, to start with, the phi xj's, as you expressed as xg plus p phi, is no longer a solution, is no longer a naive solution of the full Liouville equations of motion. So if you say that the whatever extra p's that you're going to get because of the Liouville extension is just that q kg phi plus mu gamma phi term, then you have to somehow prove that in some sense, right?
Well, okay, so what we prove is, okay, let me give a clean thing. We have so Gaussian free field with directly boundary condition xg, sorry. Okay, this is a clean probabilistic expression. Okay, I mean, this is a clean probabilistic object. So when I have functions on my boundary, I have a unique harmonic extension. So this is a deterministic function. Okay, so never mind this term. I mean, what we prove is the following. So I'm going to make a very clean statement. I take e to the alpha j and I regularize my field at scale epsilon. Okay, just like here. And I multiply by epsilon to the power alpha j squared over 2, each of these terms. here I integrate, so my Gaussian free field on my surface, it's a well-defined object. And I take plus mu e to the gamma. Here I regularize at scale epsilon and I multiply over 2. This is exactly what I'm doing here. So I have a quantity which is completely well-defined probabilistically using the Gaussian free field, but there's a cutoff epsilon, here and here. We showed when epsilon goes to 0, that the average with respect to the Gaussian free field converges to something, and it's a rather explicit probabilistic expression. So there's no conjecture in our work. We provide a probabilistic expression which is completely, which is rather explicit in terms of this Gaussian chaos measure for the correlations.
When you're taking the expectation value with respect to the Gaussian free field.
Yeah, of course.
But now you have the full Liouville thing, right?
Yeah, but I have Liouville's here.
Yeah, so what I'm saying is you have to somehow prove that just taking that extra term in the exponent is going to compensate for whatever you have done by taking the extra terms in the action in the path integral. Because in the path integral, if you have other terms, especially when you have this e to the gamma phi term, is going to alter the equations of motion in a drastic way. So in general, phi of phi is no longer going to be just the Gaussian free expression xg plus p phi. So if you're saying that
of course, these correlation functions are expression, it's non-trivial. It's completely non-trivial. Let me give you an example, okay? Let's go on the sphere, okay? Okay. If you go, let's go on the Riemann sphere, say, okay? So complex plane, and I look at the correlation functions, okay? Just to give you an idea.
Yeah.
Then nouveau partage. So, okay. Okay. Can you see?
We're seeing a part.
Can you see now? LCFT correlations are moments of GMC.
Yeah.
Okay, so here I'm sorry. So gamma and mu are the parameters, and so here I'm on the sphere with some kind of metric, which is so z plus here means maximum of z in 1. Okay. Okay, so I have, this is the expression for the correlation. So I'm on the sphere. So the points are z1, zn. Okay, n equals m, and m gamma is it's the exponential of gamma, the Gaussian free field. I get that the endpoint correlation function on the sphere with the points zi, well, it's some explicit thing times the average of a fractional power. So see, this is S is some kind of function of the weights of Q and gamma. I get a fractional average of a fractional power of this random volume form that I integrate. So you see, I don't know if it answers your question, but we get, it's the same thing with amplitudes. We get probabilistic expressions. The correlation functions, we have expressions, but they're complicated. You see, because of this term. So this is Gaussian free field, and this part here, which is the interaction part I mentioned, it gives rise to this fractional power of this random variable here. So I don't know how much it answers your question, but at the end we get well-defined objects, but they're complicated to study.
No, suppose you, instead of the e to the gamma phi, you just had a phi 4 term. Okay, so suppose you have quartic interactions.
Yeah.
So in general, if you write down say the 2-point correlator, it will have loop corrections, right? In a quantum field theory, it will have a set of loop corrections which in general can't be written in a closed form which can be exponentiated. It will have a very complicated form.
What do you call a loop? A loop is some kind of semi-classical expansion?
No, not semi-classical expansion. So when you have, say, phi, and you bring down the if you expand the exponent in the action, if you in the path integral, then you bring down the action in lieu of the, I mean, beside the phi terms, and so they will contract. They'll contract.
Okay. So you're expanding the action term, right?
Yeah, you're expanding the action in the exponential.
Yes.
So that,
okay.
So that the potential terms are brought down, and when you contract with the phi with the potential terms, you in general get loop correction.
Yes. You know, you're doing Feynman diagrams or
That's
stuff
a
like that.
Feynman diagram approach.
Okay.
Now, yeah.
So the magic here is that that's kind of one of the insights also of our work, I guess. We really do not want to expand this action. We keep it as it is. The take-home message is when we constructed sine Gordon, we're constructing cosine hyperbolic Toda field here. We certainly do not want to expand the action. We do not do that at all. We work directly with it, and we do not expand it. And the surprising thing is that we can very easily get a complete exact expression for the correlation functions. But we do not expand at all. That would be a disaster in Liouville.
No, I mean, what I'm saying is, if you start out with the left-hand side where you have the Liouville action along with the vertex operators.
Yeah. So this.
Then,
Okay, no, you're this thing. Okay.
This thing. Yeah.
So I take product. Here I take product e to the alpha.
Suppose you have phi x1, phi x2.
Yeah.
Now this S is given by this expression, d phi square plus q k g phi plus mu gamma phi. If you now really do an honest to goodness evaluation of the correlators using this particular action, then I don't think the result that you will get can be exponentiated in any simple way. It can't be. Because the phi 4 term itself can't be exponentiated.
So you want to take the correlation of
phi x1, phi x2 first.
Yeah, but you don't want to do phi x1, phi x2. You want to do exponential alpha 1, phi x1.
Yeah. So suppose you take exponential alpha 1 phi x1, alpha 2 phi x2.
Yeah.
Okay.
Yeah, that's what we do.
Yeah. So if you expand the exponentials, the first terms would be alpha 1 phi x1, alpha 2 phi x2. If you expand the exponential as 1 plus alpha 1 phi x1 plus alpha 1 square phi x1 square, etc., the first terms would be just be alpha 1 phi x1, alpha 2 phi x2.
Yeah.
You have to evaluate each of these expressions separately, right?
Which exponential you're expanding? Which exponential? The one at e to the alpha 1 phi x1, or you're expanding the action?
Both. In order to evaluate them, you have to expand them, because unless you expand them in a normal, if you don't get in the correlator form, if you don't get polynomials of phi in the expression, then in general you wouldn't be able to compute the Green's functions using just the Gaussian expression.
Yeah, I know, but the idea is that we use a completely different method. We do not expand anything, and we get.
No. What I'm asking is, how do you prove that the left-hand side is equal to the right-hand side? Is there? Are you just making a conjecture, or is there a way of going from the left-hand side to the right-hand side in a straightforward way? That's what I'm asking.
You're talking about
by the left-hand side, I mean not this. By the left-hand side, I mean go back to this is the right-hand side, and the left-hand side is the one which is on the previous slide.
Yeah, so this is the path integral.
Yeah. How do you go from the path integral to this expression? That's my question.
To the right one here.
Yeah. Because if you evaluate the path integral, I don't think in general you would get something which can be, even if you have e to the alpha j phi xj, the rest of the term, the rest of the corrections that you're saying are the perturbative corrections, the loop corrections. I presume they would be the loop corrections. But I don't think the loop corrections can be written in such a simple form, even if you have e to the alpha j phi.
You mean I have to expand this thing here?
Even if you don't expand, if you treat it as a current, I mean, if you treat alpha j as a current, as j,
Yeah.
then if you treat this as e to the j phi, and then you evaluate the Liouville action using this particular j phi, you would get a very complicated expression in terms of the j's.
Yeah, but what we do is we use a probabilistic theorem called the Gaussian theorem. It's a kind of called the complete the square trick in physics. We are able to, okay, these terms, we put them in the action here by saying that essentially phi, it's nothing but a direct mass. So and we can kind of put it in the action, and we find a meaningful limit. So I think it's going to be hard, you know, maybe to understand ourselves, but we don't. You want to. I see what you want to do. You want to expand stuff, and use, you know, rules for computation, right?
I mean, I just want a field theory sort of proof of this expression.
No, I think he has made it clear that he does not want to do perturbation theory, right, Shomadata? So I think Vincent's whole point is what you do in perturbation theory, you can't make it rigorous mathematically, and this probability theory approach is a different way to approach the problem.
Okay, one of the first things that I hear, okay, it's not an answer, but one of the first things that I hear when I talk to people in physics is they said, you did it completely the way we don't teach you to do it in physics. Okay, people expand in physics. We do not expand at all. We use the Gaussian transform. People in physics say the path integral usually doesn't exist, or blah, blah, blah. We show it does on Liouville. So I think that you really have, you know, you really have to forget, you know, all these things of Fineman diagrams, expansions. We don't use anything of this. We have a direct probabilistic expression just by using tricks which are called the Gaussian transform, in fact.
Actually, I have a quick question. So is there any new insight on S-duality or crossing symmetry type properties that you gain from the probability approach?
The point is, okay, we construct correlations using a path integral, okay? Probabilistic, and by definition, our objects, they satisfy everything you want, you know, crossing symmetry, blah, 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 because it's built in our construction. So I don't know if it's interesting for a physicist, but what it does show is, so people have tried to, you know, I think Teschner also has some kind of justification of crossing symmetry in Liouville. But what are, okay, on the mathematical side, you see what we get, and so is the following, is that you see on the left, all this is well defined. I mean, we defined it using probability theory, Gaussian and all that. And on the right, this depends on the way we decompose our surface, right? I mean, I said I decompose the surface, I use plumbing coordinates, but I can also decompose my surface differently. I mean, I can cut cycles here and here and here. So what and at the end, a priori, I'm going to get a different expression. Now, the crossing symmetry assumption is that however I cut my Riemann surface, the right-hand side, which completely seems to depend on the decomposition of my surface, should not depend on my surface. So as a corollary of our work, it is the case, because here we have a surface, we have no decomposition whatsoever of a surface on the left-hand side in our probabilistic construction. And then we decompose it with any kind of, you know, pan decomposition. We get this expression, but since at the beginning we had no pan decomposition, it means that all these quantities we have, they do not depend on the pan decomposition, and in particular, the Liouville correlations using the bootstrap, they do satisfy crossing symmetry. So a second output that I don't know if it interests physicists or not is that I know no proof, and I've asked lots of people, of existence of the blocks. meaning that it's a power series in Q, right? Because it's a holomorphic expression in Q. But if you look at the coefficients of these guys, they're very complicated, you know, and involving the Virasoro algebra. And by hand, bounding the series is actually difficult. And there's no direct proof. And since we have this expression, in particular, it proves that, okay, for almost all parameters, this thing is finite, right? Otherwise, our correlations on the left would be infinite. And so we have somehow an indirect proof that these conformal blocks, they are convergent, they exist as holomorphic series. So in some sense, we have, you know, existence of blocks, existence of crossing symmetry from our proof. We get this for free. So maybe for a physicist, you'd say, okay, of course blocks exist. Of course, Liouville is crossing symmetric, but from a mathematical viewpoint, it's not at all clear. I mean, for us.
But your proof would still be for real momenta, real alphas, right?
Yeah, right now it would be, no, our proof is for real alphas. Yeah, this is restricted to, here we don't put Q plus IPs, if I mean.
Yeah.
No.
I mean,
yeah,
because
but then, okay, if you could show, okay, it's true, but if you could show some kind of analyticity property, then you could recover it for all momenta, right?
Right. Yeah, that's usually the argument.
Yeah, I mean, if we have it for real alphas, that we have these crossing symmetries, yeah. So if then one could be able to say, okay, conformal blocks are analytic in the weights, in some sense, then it would extend. Yeah.
Right. I mean, the whole crossing symmetry thing for higher rank is much more interesting and complicated. Like depending on the Pan's decomposition you choose, sort of the number of coordinates that you assign to each node, if you wish, in the Pan's decomposition, it can sort of look different depending on the Pan's decomposition. I don't know if you've thought about it in a higher rank. So
what is higher rank?
Like SL3 or SL4 Toda theories.
Ah, yeah. So this is the kind of stuff that, okay, our student Baptiste is going to, I mean, he just did the first step, you know, kind of.
I see.
Yeah. So, I mean, if you send me references, I would be glad. But what is sure is that this thing where we glue, these gluing axioms are robust. And I'm sure we can prove them on Toda.
Okay.
So I'm sure we can say lots of things on decompositions in Toda. I mean, we can, but roughly, you know, do anything with respect to this Seagulls gluing axioms. So I mean, send me references. I mean, we would be glad for higher rank.
Sure. Yeah, I'll send you.
Yeah, and so okay. I'm sorry because I think it's some data Bhattacharya, sorry, who's asking lots of questions. I don't know if he got convinced, but I mean, no problem if you can write to me, or I don't know, we can discuss some other time. I mean, for just
sure, I'll write to you.
Okay, it's just one thing that maybe I should emphasize is that people were very suspicious on our work in 2014. People thought that we didn't define Liouville or something was wrong or blah, blah, blah. And it took us a few years to convince people that we had constructed, essentially it's when we proved DOZZ formula, I guess, that people said, okay, you have really constructed the Liouville field theory.
Great. Thank you. Thank you, Vincent, for answering all questions patiently. Yeah, so we'll thank the speaker once again.
Thanks a lot. So as I said, I'll send you the link to the IS. I mean, it's the same talk, but more time with drawings, etc. Okay? Sure,
please.
It could be, okay, maybe appreciated. And thanks a lot. And sorry that I had to cancel last time, you know, but it was great discovering my first talk with people in India.
Okay, awesome. It was awesome having you here. Maybe we'll see you in person sometime.
Yeah, so I'll be in Varsovie. Maybe I'll see someone. You know, I'm talking of this at the String 2022. So
String Math? Yeah.
String Math 2022 is in Varsovie, and I'll be there. Yeah. So maybe I guess the audience here could be there. I don't know exactly. I mean, Okay.
Yeah.
Okay. Thanks.
Okay. Thank you. See you all.
Bye. Bye. Yeah.
Thank you, Vincent.
Bye.
Bye.